Good afternoon, everyone. By the way, I'm going to be using Slido for the questions. I'll try and leave some time at the end for questions. But if I do run out of time, I'm going to try and screenshot the questions that are posted there and maybe answer via Slack or something like that. So, also, please feel free to stop me during the hallway track. I'd be happy to answer questions or if you have any feedback. All right, so quick introduction about me. So I actually asked my kids to do a drawing of what I do for a job. So this is what my 4-year-old came up with, 4-year-old daughter. So apparently this is her in green and I'm in blue and she's sitting on my lap or on my knee while I'm typing at the computer. This is my 5-year-old son's interpretation. This is me with my headphones on, typing at my computer. I work from home remotely. I also especially like the binary that's on the screen, although truth be told, I don't actually look at binary on my computer screen all that often. And finally, my 6-year-old daughter, she's decided that my job is to sit at our coffee table and do Legos with she and her brother and sister. Well, I certainly wish that was what I did all day, but here's a different take. I'm a principal software engineer at Viasat, Inc. I'm also a PhD candidate at the University of Texas, Arlington. And there's a chance you may have heard of a couple other projects I started, NoVNC, which is a web browser-based VNC client, and the Make a List project. Just a note, this talk is derived from some of the research that I'm doing for my PhD. And the challenges and solutions that I'm going to describe in this talk apply to a number of different systems, but I'm going to focus on browser render testing as the concrete example. So let's jump in. All right, so what's the problem that we're trying to solve? Well, there are some types of systems that are really hard to test, and they can be hard to test in a couple of ways. I mean, there's lots of different ways they could be, but the ones that I'm focusing on are the test cases. This challenge is that it can be hard to find or generate interesting test cases. And by interesting here, I just mean test cases that can actually trigger bugs. And the second major challenge that I'm focusing on is that some systems are hard to verify. The magic box that tells you whether the system under test is working correctly or whether it's not working correctly is often called the test oracle. And so if we want to have a fully automated testing system, both the generation of the test cases and the test oracle need to be fully automated. But if the software to automate those steps ends up being almost as complex as the system that you're wanting to test, then you have a problem. So that brings us to browser rendering. So here's an example web page. This is fairly trivial, but even this page is fairly difficult for a test oracle to determine whether this is rendered correctly. And there's a bunch of reasons for this, and I'll touch on a few. So one of them is that the CSS, the cascading style sheets, element sizing and positioning standard is fairly large and nuanced. It's also one of the basic things that we want to test in browser rendering. There are environmental factors like the geometry of the browser window, and what operating system fonts happen to be installed. The color model, the test oracle needs to correctly simulate the color model and things like alpha blending. Font rendering is a fairly big problem because subtle differences in kerning and spacing of the fonts can shift elements on the page such that they fall off to the next line and your whole page looks completely different. So a lot of the current solutions to browser testing, render testing, often involve manual user intervention at some stage of the process. And a lot of them also use a fairly constrained test environment. So can we do better? Can we do browser testing in a way that's fully automated without being narrowly constrained? And I think we can, so let's talk about that. So the solution that I looked at in the research that I'm doing has three major components. The first is property-based testing. The next is grammar-based input generators. And the third is consensus-based test oracle. So let's consider each one in turn. So property-based testing, or PBT, this is a testing methodology that was popularized by the quick check system that was developed by Ken Clausen and John Hughes in 2000. And in property-based testing, the tester defines properties or assertions about the input and output values of the system under test. The input properties define the range of valid inputs to that system under test, and the output properties are used by the test system to validate outputs for a given set of inputs, or basically the output properties are the test oracle. So when the output properties are violated, then we know that the corresponding inputs are considered a failing test case. So a typical PBT system defines input properties in terms of generator functions. Generator functions can be combined to create compound generators, and they can be recursive. And each input property generator function takes a size value along with a random seed. And that size value has a meaning that's specific to that generator, sort of a complexity value, if you will. A single run of a property-based test involves calling those generator functions with larger and larger size values. And you do that, and that's basically stochastically generating random inputs until the output properties are violated, and then you know you found a failing test case. All right, so property-based testing is really effective. I can speak from personal experience. Really effective at finding bugs. But the problem is if your test case or your bug is buried in a 30 megabyte test case, then it's not really that useful. Or it's worse than useful because it's just noise. And the highly recursive nature of HTML, the HTML grammar means that generated test cases can easily get very large. And there's actually a positive aspect to this, which is that that large test case means that you have, just in that one test case, you have really broad coverage, code coverage, potentially. But the major downside, of course, is that those large test cases aren't useful for root cause analysis and debugging. So in most property-based test systems have a test shrinking functionality. And this functionality can significantly reduce the size of the test case while still preserving the failure. And so how does that work? So we can think of each test case basically as a tree of generator functions. And so what the shrinking process does is it basically picks an arbitrary node in that tree, and it tries it with a smaller size value than it was originally called with. And if the resulting test case is smaller, and it still fails, then it continues trying to find smaller test cases. If it passes, if it passes, then it backtracks. And this process continues until some sort of minima is reached. All right. So let's consider a simple example of property-based testing. So I'm going to define our input property P as a sequence of integers. And the output property is the sum of those integers in that sequence. So here's some Clojure code. Clojure has a test check library, which is an implementation of property-based testing. I've deleted the namespace imports, but this is the majority of the test. So first what we do is we define the system under test to be the application of sum to a sequence. And so that's that. And then we define P to be a compound generator, which generates a vector of integers. The output property states that the execution of the system under test on P should have the exact same result as applying a sum to the values in P. Then we define our properties using the propsol function, implementation detail there. And finally, we call the quick check function and we request it to run 10 test iterations. And finally, it outputs basically the result. So there were no failures found in this case, which isn't surprising. And even if we increase the number of iterations to 100, we see that the result is unchanged. And like I said, that's unsurprising because we've defined our system under test and our test oracle exactly identically. So let's change that a little bit. So let's introduce a bug in our system under test so that if the system under test is run with a sequence of integers that's between 13 and 17 long, then the result will be a nil value instead of the sum. Our properties remain unchanged. We can see that running 10 test iterations with this new buggy system under test still pass, and the reason is because the size value, it didn't generate a sequence that was long enough to trigger the failure. But if we increase our number of iterations to 100, we'll see that on the 31st iteration, the output property was violated, and we found a failing test case. And this is the sequence of integers, basically the value of the test case that caused the failure. Then the system continued and it did 262 more iterations to try and find a smaller test case. And it ended up finding that a sequence of all zeros, of 13 zeros, would trigger the problem. So you can see that that's a lot less, in terms of complexity and size, it's smaller. All right, so now let's talk about how we do the input properties for browser rendering testing specifically. So in this case, we want to generate web pages, which means generating HTML and CSS. And those basically correspond to the content and the presentation of a page, respectively. And there's a third component of behavior of a web page. It's typically defined in JavaScript, but that's out of scope for this project. All right, so our basic approach is that first we download and normalize, basically from the web standards, we take data from the web standards and normalize that into spec data. Then we take that spec data and we translate those into eBNF grammars. It's sort of a standard language for context-free grammars. Then we take that grammar, eBNF, and we translate that into closure generators, generator functions in test check. And then we take those generator functions, and the test system loads those and uses those to generate our final test cases that it's going to test with. So for a concrete example of this, I'm going to show just a part of the CSS standard, the cascading style sheet standard. And the bulk of the standard is actually dedicated to defining CSS values. And CSS values are defined using a bespoke grammar that's called value definition syntax, or VDS. The grammar is somewhat similar to eBNF, but it has additional combinators that are optimized to deal with the ordering and repetition flexibility that CSS permits in the values. So here's an example of the VDS definition from the CSS spec for the text emphasis position property. This are the values that are allowed for that. And this definition basically states that the value should be either the word over and under and then the word right or left. And here's basically the equivalent eBNF grammar that was generated from that. Then we take the eBNF grammar and we translate it into closure test check generator functions. And so here's an example of that. Just a note here, that frequency generator, that's a test check built in. And what that does is it basically selects between other generator functions based on weight values. And so you can see that 100 is the default value here. And so it's going to do even 50% chance choice between the over, under, and left, right pairs. All right, so one of our goals for the overall approach is that the system is controllable. And one of the ways we accomplish this is we have tunable weights associated with each branch point in the grammar. And by tuning that grammar, the tester that's using the system can decide what sort of testing they want to perform. And some examples of the different kinds of testing they could perform by tuning the grammar is single component testing. They could avoid known failures. They could do pairwise or combinatorial testing, or typical and atypical test cases. So here's the grammar I just showed, but this isn't actually complete yet because it's omitting the tunability. So if I add, this is the final emitted grammar, what it looks like. And you can see here what's changed is that we're doing a lookup in the weights value here. It's a lookup table, and it's basically overlaid the default weights, and it's merged in with the weights from a configuration file that the tester can define. All right, and this is just an example of what that file looks like. This happens to be closure EDN format. In this example, I've actually modified the weights to make the over and right words appear twice as often as the under and left case. Okay, so now it's time for a little bit of demo. So I'm going to demonstrate what I've showed so far with basically property-based testing and the grammar-based test case generation. So this part of the project was actually generically useful, and so I split it out into a different project called InstaCheck. So let me see if I can get this to work here. All right, cool. All right, so let's look at a simple eBNF grammar that we're going to use to generate our test cases. So what this grammar does is it basically defines a file, well, a test case that contains whole numbers that are on lines by themselves. But I won't go into that too much. All right, so I'm going to run my InstaCheck project. I'm going to give it the grammar. And for the first thing to demo, I'm just going to have it generate samples. It's not actually going to test anything. It's just going to use the grammar to generate some examples. So if I look at, oops, compare the first and the last examples that it generated. Okay, so on the left is the first sample it generated, and as it generates samples, it's using increasing size values. And so on the right, you can see that it generated larger values there, and more of them. So I actually have a configuration file here, and it's already modified. So I'm going to increase the number 7 in this grammar so that it occurs 10 times as often as it would by default. So now I'm going to run that same one, but I'm going to specify a grammar file. I'm sorry, a configuration weights file. Look at the samples again. And you can see here that 7, because I adjusted that weight, now it's happening almost half the time. So it's just an example of tuning. All right. So before I get to the actual testing, let me just show one other thing here. I'm going to use that same grammar. Whoops, but I want to change my command here. I'm going to ask for closure code. So this is going to output the closure equivalent. The generators that it's actually using underneath, but it's outputting the code. So this is closure code. If you're familiar with closure, it shouldn't be too hard to read. But basically, this is the code, the equivalent code that represents that grammar for generating test cases based on that grammar. All right. So let me go on to the next part. So I have a little more complicated grammar here. This is basically going to generate simple math expressions of increasing complexity. And then I also have a test program here. It's just a shell script. And in this shell script, I define 2 functions, the system under test, and what I've made the system under test be is basically just a Python expression evaluator. And then I've defined an oracle, and the oracle is basically a Ruby version of the same thing. And then at the bottom here, the last line is basically saying, run the system under test with my input, my test case, and compare it with the oracle to see if they're identical. So now I'm going to use InstaCheck with that grammar. I'm going to give it the template for how I want to generate my samples. I'm going to generate 50 iterations here, or it's going to go 50 iterations before it stops if it doesn't find anything. And then I tell it what command I want to run to test with, and template again with the test case. It's going to fill it in here into the command. So let's run this. All right, so I was running the test, and it's going by pretty fast, but at some point it actually ran into a failure, and so it's actually going beyond 50, obviously, because it hit a failure, and now it's doing the shrinking process. All right, so here's the full result at the end. In the middle there is the failing test case, the expression that it found where the system under test and the oracle differed. And it hit this problem at test case 36. And then at the bottom, near the bottom, you can see the smallest version of the test case that it found that still triggered the problem. So I'm actually going to use an alternate version of my test program that just is more verbose. And run it on the first failing test case. So those are pretty long numbers, and it's a little hard to see what's going on there. I mean, if you look at it for long enough, you could probably figure it out. But let me actually use the minimal shrunk case that it found. So with this shrunk case, we can see that there's probably a mathematical precision either on the calculation or the printing out in one or the other, or both. But that's an example of how what the shrinking looks like. All right, let's see. So one more thing I just want to show here. So this is the grammar. This is automatically generated from the specification data. This is the grammar for HTML. And so it's fairly long. And I want to do, I'm gonna just generate samples from this HTML grammar. There are almost 500 rules, grammar rules in this file, so it takes a few seconds to run to generate, to load that. It doesn't take as long if you actually use the Clojure code directly. So let's just have a look at one of these. So there's no indenting here, obviously, but this is one of the HTML test cases that it generated. All right, so let's see if I can get back to my presentation here. All right, so here's another, just thought I'd show another piece of artwork from one of my kids. This is my 5-year-old son, and it's a description of what this project is about. So I've covered how we generate test cases using grammars and use property-based testing to run tests against them. So we have a way to do that now that's automated and controllable. But the question is, how do we determine whether a browser has correctly rendered these test cases in an automated, controllable way? So the key insight here is that this type of difficult-to-test system, there's a subclass of those in which there are multiple implementations. And this is particularly true in the web browser space. You know, we have a few implementations. In fact, we really have a surplus of implementations in the browser space. This is an example of this is an indented test case that was generated by the system. And here is screenshots of that test case rendered in 3 different browsers. It's pretty clear just from visual inspection that Servo, by the way, is a new development browser being developed by Mozilla. And it's pretty clear from this that the Servo browser is different than the others. It's not immediately clear, though, whether Chrome and Firefox are different. And so let's move these around and then insert difference images. So what this is doing is subtracting the color channels for each pair of browser screenshots. And so the black areas represent where there was no difference, and any other colors represent some sort of difference between those pair of browsers. So now it's pretty easy to see that the Servo Firefox and Servo Chrome difference, there's pretty significant difference there. But we can also see, it's a bit clearer now also, that there is some subtle differences between Firefox and Chrome. But this actually raises the question, are Firefox and Chrome actually different? Is that a failure? And so, now we ask the question, do we have consensus? And there are actually numerous ways of comparing images in the research literature. There's even some literature, discussing how to use machine learning approaches to be able to determine if 2 browsers rendered a page in a way that's indistinguishable to the human eye. But the fact actually is that a tester is probably going to want to control this. They're going to want to, depending on what they're trying to accomplish, they're going to want to determine how browsers' renderings are compared. And so for this research, we found that just using a squared sum of differences of the difference image to get a single value, and then comparing it to a threshold value was sufficient to validate the approach. Okay, so now we have an answer for whether each pair of browsers are different from each other. With 3 browsers, there are obviously 3 different delta images. And so the question now becomes, what if they disagree? And there's some different categories of disagreement. You could have what I just showed, well, kind of, where 2 browsers basically are in agreement with each other, and there's a single browser in the case of 3. But basically, you could have a single browser that's different from all the others, and all the others are self-similar to each other. So in that case, it's not, this isn't a proof that browser is doing it incorrectly, but especially in the browser case, we're often more interested in, is it the same as other browsers, rather than is it like mathematically correct according to the standards. So So if there's one browser that's different, it's pretty clear that it's a fault. But there's some other cases. We could have a case where all the browsers are different from each other. And that's pretty common, actually. And where this happens is where you have web specifications or lack of a web specification for certain elements on the page, or the specification is vague. It's one of the common cases where we found that. And then there's some interesting cases where no browser is at fault, actually. Or there's no obvious browser at fault. So one example of this is where we could have browser A and browser B. Their difference is below the threshold. Browser B and browser C, their difference is below the threshold. But then when you consider the difference between A and C, the difference is now above the threshold. And what's happened is basically B has sort of split the difference between the two different renderings. And so, what does that mean in that case? And really, the answer is that it depends on what you're trying to test. And so you really want, the tester really wants to have control over the meaning of the consensus. All right, so just real quickly, I'm going to go over the architecture of our testing system. So on the left is, I talked about this, where the Mozilla Developer Network actually has some of the best sources for specification data in more programmatic form. So we take that data and we run it through an automated process that basically generates our grammars and our generators, and we store them basically in our data store. And then on the right, we have, at the top right, is basically our browser consensus pool. Our system has an embedded web server so that the browsers can load those test cases from the data store. And then the green box inside the larger one on the right is basically our test driver. And what that does is that connects via the WebDriver, the Selenium WebDriver protocol, to our consensus pool. Tells the browsers to load the current test case being considered. Once that test case is loaded, then it screenshots all the browsers, stores that to the data store, generates the delta images, and does the comparison for consensus or not, and stores all that, logs all that data, including the delta images, to the data store for review later. All right, so let's do our next demo. Okay, so I call this part of this project Tend. There's not really a good reason for that name. Historical reasons. I may change it at some point, but this is what I'm showing here is just a configuration file for our testing system. Those are different categories of configuring the system. So this is the quick check or the property-based testing configuration. Then we can specify a weights file for configuring the weights that we want to use. Here's our comparison configuration for comparing images with our threshold value for after you get the squared sum of differences that we compare it to this threshold value to determine whether those browsers are different enough from each other. The embedded web server and data store configuration, and then the configuration for the browser consensus pool. And by the way, the project does support pointing at browser stack. So you can use different versions of arbitrary browsers that browser stack supports without having to run the test harness or the test drivers for your browser locally if you want. Okay, so I am going to start a test run. Oops, come on. Okay, so this is going to start up. It's going to start the embedded web server. It's going to load connect to the browsers in the consensus pool, and then it's going to start generating our test cases. So you can see that we're already up to the 5th test case here, and we already found a violation there where there's a disagreement. All right, so let me see if this will work. Okay, so here's a report page. So the embedded web server also has a reporting mechanism, so it can show you status of the current test run. So this also has establishes a WebSocket connection to the server and dynamically gets the test information as it's being updated and updates that on the page. So on this page, what the columns are showing here. Let me see. This is a little bit tricky, but let me see if I can hit the. mirror image. I'm not used to this. Okay, there we go. All right. So the different columns here. So on the left is the current test iteration number. The green and red colors represent whether the test cases are passing or failing. And we can see here that on the fifth iteration, it hit a failing test case where the differences were greater than the threshold value we set. And then there's also, so the first few columns are the screenshots of the browsers in the consensus pool. There's an average column, and then the rest of the columns are the difference, the delta images. In this case, there's just one delta image because this is only showing 2 browsers. All right, the test actually finished, completed, and in the on the top there's a summary line that shows. One of the most interesting parts is that it shows the initial test failure, the number of bytes, and shows the shrunk number of bytes that it was able to reduce the failing test case to. Okay. All right. Oh, okay, good. Hello? No, don't do that. No, don't do that to me. Okay, maybe didn't do this before. All right, well, we'll try and keep going even if it's switching, just so we have time. All right, so finally, I couldn't resist throwing in one more. This is my 6-year-old daughter, asked to describe what this is about. And I think it's about as accurate as anything else, so. All right. So let me just review real quick. The challenges of browser render testing that I've addressed basically fall into sort of 2 categories: the automatic test case generation and the test oracle. And you can kind of sum it up as end-to-end test integration or test automation. And there are 3 basic components to the solution that I'm proposing, which the first is property-based testing, and critically important there is test shrinking. Grammar-based input generators, and there's the standalone project that can do property-based testing of grammar-defined inputs called InstaCheck. And then the consensus-based oracle to be able to automate the determining whether the case is correct. Okay. And that's all I have. Just a few links where you can go for further information. So this presentation itself is at that first link. And then the projects are the next links. My Twitter handle, email. And also I'll throw in a plug here. I work, like I mentioned, at Viasat. And it's a great company to work for. We're doing really interesting stuff. And also we have satellites in space, so there's that. But if you're interested at all, check out the careers page. And finally, just I want to call out thanks to the chair of my dissertation committee, David Levine at UTA. So I think we have a few minutes for questions here. So let me pull up the Slido page, see if it'll update. Maybe. All right. Okay. So do you see applications of this work to testing websites themselves in addition to browser rendering engines? It's a good question. Yeah, I think it could definitely be used for that. Yeah, I think it wouldn't be that hard to basically swap out the grammar generator and just have a corpus of the web pages or have something serving up the web page. One note is that this is a fairly static web page, so it's going to be more useful for testing the rendering. So there need to be, if you wanted to test behaviors, there'd be more work that you'd have to do for sure. But it should be pretty easy to plug in if you want to test web pages rather than browsers, for sure. All right, let's look at another question here. Do you have any tricks to simplify the generation of tests involving dependencies between CSS properties, e.g. z-index requiring a non-static position? Right. Okay, so what this question basically gets to the bottom of is that the grammar language that I'm using is context-free grammar. So there isn't a way to have it reference some other thing that you've already generated. I think the architecture of the system itself is pretty generic. So you could plug in a different grammar language and then translate from that to the generators. Because the generators, the closure generators could easily support context, but the grammar, EBNF grammar itself is context-free, and so you can't have, generate something and then generate something based off of that. So the answer is the current system, no, you can't do that, but I think it would be pretty easy to swap in a different grammar language to generate. Not easy, but it's definitely possible. All right. So do any of these test failures translate into high priority bugs, or is it mostly finding edge cases? That's a good question. This is actually an area of ongoing research. That's in a sense the next area that I'm really going to do is try and run this and tune the system to be able to really find bugs. I have actually found the reason why it's only showing in this demo, only showing Firefox and Chrome, is because in running the system, did discover a bug in Servo where it crashes after the 12th screenshot. And this only happens in headless mode with, I think, just with the WebDriver protocol active. So that is a real bug, and the system did find that. It wasn't the type of bug I was looking for, obviously, but it did find a real bug. I suppose it is a question: is disagreement between, say, the applet HTML element, which is an obsolete element that you probably won't find. That is, all browsers basically disagree on how to render that, even when there's no applet being run. And so, I guess in one way that's a false positive, but it really did find a difference, and it does quickly find differences between browsers, and they are really legitimate differences. Let's see. Does anybody in the room have questions that they weren't able to ask using the Slido app? Yeah.
How much time do you have to spend on testing your Oracle? So what if you've written your Oracle wrong?
Yeah. So the question is, how much time do I have to spend on testing the Oracle? I think that would be more applicable if the Oracle was actually doing some sort of logic about the page. It's more relevant when your Oracle actually has logic that's trying to verify the system under test. In this case, there was a lot of work I had to do to get to normalize the screen captures and get it so they're actually comparable, of comparable size, so there was a lot of work there, but it wasn't so much in the Oracle algorithm itself. The Oracle algorithm is pretty straightforward, right? It's just screenshotting the images, getting the deltas between all the screenshots, and then doing a squared sum of difference and comparing whether they're different. So I use OpenCV for a lot of the image processing stuff, and figuring it out took time, but I didn't have to spend that much time debugging it once I got it working. So, but yeah. Yeah, so the way I got around that is that I didn't develop the grammar myself. There's a few headers to the grammar that I put in myself to load like some standard normalizing CSS that a lot of pages use. Because browsers, for example, have differences in what the margin and padding defaults for the body is. And so I need to normalize that. So that's hard-coded in the grammar. But the rest of the grammar is actually generated programmatically from specification data. And that's actually a good point. I did find some bugs in the specification data itself that not the web standards, but the way they were imported to the Mozilla Developer Network had some errors. But yeah, I mean, that's a good point that, you know, if your inputs are really complicated and creating the grammar for it, you know, if it doesn't exist, or if, for example, it's not context-free, then there's work there to be done, obviously. So, yeah.
This seems pretty close to being able to look at a web page and generate code for it. Does that seem wildly different than this, or close to it?
So the question is being able to look at an existing web page and generate the code for it. Yeah, so actually, that's a really good question. The next step in the research is actually to be able to look at a corpus of web pages, which may be just one, and use the grammar, because we have a grammar for a web page now. And I actually have some patches to the instaparse library, which is the library underneath I use for the grammars. And what it does is actually logs the path through the grammar and generates a weights file based on that page or that set of pages. And so then you can take that weights file, turn around, use the system, and it will generate pages that have similar types of elements on the page. So, and I've done that some. It's still, you know, I'm 75% of the way done. Cross my fingers with that, but yeah, it's a good question. It's the next thing we're working on. Okay, yeah, that's just one last question.
So when you generate from a grammar or any recursive type, the same weights at each level, then it's quite easy to make a generator that either loops infinitely or generates extremely large data. Have you got a trick you're not telling us about?
Yeah, good question. So the question is about if you have a recursive generator, you know, how do you avoid basically falling into the case where you don't have, you know, it just keeps going forever and you get a 6 gigabyte test case. And the answer is I cheated and used the test check actually has a lot of the property-based test systems have a way of generating recursive grammar. So they actually have a generator that says, here's the outside, here's the inside part. And it actually, it prevents you from going infinite. So it uses the size value to actually determine how far it recurses. So, all right, well, I think I'm out of time. So, like I said, if you have any more questions, please feel free to stop me. I'll be down here for a few minutes. Although I think that probably the next presentation is up, so.